It just makes sure we're all working on the same map. Either one can be used, but we have to update all the locations to the new one in order to use the new reference. And these locations are all based on the previous one. But it doesn't really impact the analysis for what we're doing and what a lot of things do, as long as you know what reference you were actually using. So you want to be using, I think it's September 2001, like on the screen, use CamFab 3.1. And what we're going to be doing is designing primers for long-range PCR, as I said earlier. So you want to choose the link for chromosome 5, and you want to zoom out 1.5x. Please only hit it one time. 1.5x. That's it. If you hit it twice, you're going to be further than you realize. Make sure you're on CamFab 3.1 and type in all the stuff that's on the previous slide, and then just pick the chromosome 5 link and zoom out 1.5 times.
I'm not looking at it. It says chromosome 5.
If there's 5 of them, are they all in the dome?
No, I actually have a point on this. My mom tried to do what I was doing. This is really kind of vague. No, it's like independent race. She did chemistry and biology, but like she still does. I know, it's crazy.
Alright, so we zoomed out.
And you can set it up. You guys can get that a little bit. You can show different isotopes. You can get rid of certain tissue groups. You can get rid of you can do comparison across species. So it's super to use. Like all the stuff you show with little boxes that you can show and hide. So you can just start playing with it.
Chromosome 5. Hand up. You can still do that. So what's going to happen is there's going to be different settings for the
legacy of the job.
So like we're still looking at the same location. Zero might be slightly. There's some different isoforms and not, and some people may have already picked it, like the bulk setting, maybe that.
Oh, right. That's always
It's just these options here. Yeah. So you might start playing with these, you can pop up and go away. Okay, hopefully everybody is zoomed out 1.5 times. It's okay if your screen looks a little different than what's on the screen here or from the person sitting next to you, because as you will find, there's lots of functionality of these genome browsers, and you can show different isoforms, you can eliminate different isoforms, you can show different species for comparison, you can eliminate different species for comparison. So you're going to want to click on the View tab on the blue bar at the top, and then choose DNA sequence, choose Get DNA, and then open a new browser tab. I'm going to open it in a new browser tab.
That's a lot, isn't it?
Yeah.
That's okay. Dad, you can be right before my mom. Need a little bit of me.
So hopefully you see something like this when you capture the DNA. So how many of you are seeing different, everybody listening, how many of you are seeing not quite the exact same sequence captured with your neighbors? Why do you think that is? Well, most likely it means that when you zoomed in or you zoomed out, or the specific isoform you typed in is slightly different than the one that your neighbor picked up. Remember, he said there's different isoforms. So if you zoom in and zoom out and you're capturing everything, it's going to capture almost everything in that region. It's fine. It's not going to affect what we're doing today. So it's okay if it's slightly different. So everybody looking at what I see here on the screen? Me as well. Yeah, I see some already. All right. So you're going to need to go to this website. Again, there's a lot of you in here. You're going through it at the same time. It might get a little glitchy, but just be patient. And you want to cut and paste all of the previous sequence that you just captured from the website into the primer 3 box here. So pretty much the big window where you can cut and paste stuff. Okay, once you've kind of pasted this in there, some of you may have already jumped ahead a bit. So primers require around 20 base pairs from each end of the region that you wish to capture. Now we try and avoid repetitive regions, so regions with lowercase. And we typically also try to make the fragments that we get smaller than 800 base pairs. Okay? So if we need to capture a larger region, then we use overlapping sets of primers, or primer pairs, and we allow the captured portions, so the bits between the primers, to overlap by around 50 base pairs, but less than 150 base pairs. Okay? Because it's such a big region, we use multiple primers to capture that region. So in the Primer 3 software, you can just let it design primers without your help, so accept all the defaults. And this will return a maximum of 5 primers per side. What do I mean by per side? Anybody? Yeah, exactly. So we're trying to capture a certain chunk of DNA. So when we say per side, we mean basically from the forward, so 5' to 3', and from 3' to 5'. So you can do this by accepting the defaults. So you can try it by selecting pick primers. Now the only problem with this is that it often puts the pairs of primers too close together to be useful. Right? You can see where it puts the primers in the sequence because it underlines the sequence with little arrows. The direction of the arrows show the direction that the primer will be read, and the captured piece lies between the two. So the piece we're interested in lies between the two. Now primer 3 shows you its favorite pair of primers at the top of the page, but it shows alternative primers at the bottom of the page. So has everybody got everybody seeing what I am seeing on the screen? Little arrows? Did you scroll down enough? They're not there? Remember, remember we said it puts the primers often too close together, so they might be right next to each other somewhere, depending on the size and scope of what they're at. Yeah, I see people have found them. Just gotta scroll a bit. Okay. Yeah, so clearly you can tell by the example that's on the screen that I knew I'd be showing this class, so I put it at the very top of my output file because I'm lazy. Alright? So, what do you do if you want to push the primers to the edges of the sequence that you wish to capture? So you want to push them to, like, hey, look, I want the sequence, but I don't want the primers overlapping the part that I'm interested in. Well, in this instance, we use square brackets to exclude portions of the input sequence. So you see in the example on the screen the square brackets. So you can hit the back button on yours, and you'll go back to where the sequence is already in there, and you can add square brackets to exclude that part of the segment from being affected by the primers, basically. So you can say, look, make sure I get some primers in here, but do not put them in this area. So in this case, what you see here on the screen, we are excluding the second, third, and fourth lines of sequence from being allowed to contain any primers. So everybody see the square brackets? Yeah. Sorry, I can highlight it here, makes it a bit easier. So the sequence that you have in the window is too long for a standard PCR primer, which I'm sure most of you have seen now, given how far you've had to scroll down. Okay. So we might like to exclude the piece in between our desired primer locations with the brackets, and also the latter part of the sequence that we will design the next primer to fit into. So if we were trying to capture all of what we've got, we need multiple primers. So we would exclude certain parts of the sequence so we can set the primers where we want them to be at. Really important if you're trying to capture a specific part of the gene or a specific gene itself, and you're looking for a specific variant for a genetic test. So you want to be able to exclude that specific variant itself and just capture the flanking regions. Alright, so sometimes primer 3 restricts how many selections you can make. So if you like, you can just capture all of the potential left primers through the region and then choose the one that you like best. And you can also repeat the process and choose just the right side primers. Right? And these are the different options that you accepted by default earlier. Now this is done by unselecting the pick left primer or use the left primer only checkboxes. So if you look at the options, you can have a play with that. So what I want you to do is see if you can move the primers. We'll give you about 10 or 15 minutes. Move the primers to an area that you specifically want to capture in that gene. Right? So can you alter the primers and let's say capture the first part of the gene using 2 different primer sets? Does that make sense, everyone? Right. First part of the gene, you can pick which part you want specifically. Right. But pick apart and see if you can set the primer so that you capture that sequence using the the data that you have.
No price stuff.
How do we decide which one to exclude?
Yeah, I'm really sure. I didn't get that. We'll talk with just like getting the stuff which like I indicated.
Is that up to put in a bracket?
Yeah, I put in the brackets of those well the locations you sent to, and that's what I got. So I don't know if we're can't see any other ones though. So yeah, I'm not sure where else. I don't know if we're just like fiddling around with it and just like excluding random sections or.
But if you exclude too much, you're going to have
Okay.
and also it's different stuff. I was like,
Right now. I lied. I got an extra one card. You're trying to find it. Yeah, sure. Well, she knows. I like and then yeah, that's where it's good that you get to say I'm working just like yeah. like obviously at home, yeah, I was really like ethics day on AI. Yeah. I know. It was so good. I was expecting it to be more like real, but it was actually like more philosophy. And the class was like so interesting. The class was much longer than what I expected it to be. But yeah, literally like we're going to class from 10 a.m. to 1, and then we have a discussion class after that. So like that's the majority of your day. So like what are you listening to? But we were clubbing at night, class in the day. So like I think every single day. We went everywhere. Ministry of Stamp, we went like
I didn't hear it properly. Okay.
Yes. So I'm a bit confused about what we're doing. So basically we're trying to design the primer, right? For this sequence, right? So remember, but that's a huge gene. Right. So there's no way, it's too big for a single primer set to capture, right? Yeah. Multiple primers will be needed to capture the entire gene, right? But let's narrow it down to less than just a gene. Let's say we're only interested in a certain part of the gene.
and it's so cheap. In our university, we were literally sitting and studying for exams in the bus.
And a primer to capture that part of the gene, right? And the primers are almost flanking the part we're interested in. So what happens if it puts the primer in the part we're interested in? Yeah, right. So it's only going to show us part of what we actually want, right? So the square brackets allow you to.
Yeah. Oh yeah, we do
For that. Now, it's going to give you multiple options. It'll give you the best one that it thinks is the best first. If you scroll down to the bottom of the output, it'll give you a bunch of other options. You can kind of look and see which one best fits your interest. So you just have a little flavor like, oh, what if I want to capture something in this sequence? Yeah, so you can see there's more here. The primers are here. Right. So the next step, we're actually going to use those primers.
I love
So you want to, yes, you want to so it depends on what you're looking for, the size of the region, how comfortable you are with technology, the accuracy, things like that. Oh, right. But it's just going to give you options. So I guess something good was there. It's just stupid computers. They're stupid computers. You still need to look at it and be like, all right, this is still a dumb option. I'm not doing that. Okay. So even though it's like, this is the best one, you're like, I still know.
was so good as well. We went to exactly optimized.
You run the primers already? So you have the big primers, okay, so get out there, you can try to get some primers.
I was going to do it with my friends, but then they were planning a big paragliding. So like, my friends about that, my friends were like, no, you can't do paragliding in the and so I'm like, yeah, if you want to go, you can go with the honestly, the best of my life. My friend, my mate, we're planning on doing these
run it, and then we'll put the primers around that section. No, like, so let's just say you're interested in this, you want to capture, let's say, the third, fourth, and fifth row. So you put a square bracket to start, and then another square bracket at the end. and then run it again. And now it's going to, where the star is, it's going to exclude primers, but it will put the primers on the other side. So we just say, hey, don't put the primers here, I want this redo. Put it around that redo. You know? And then you'd have to, but remember, this is only a small part. You still need to get this. You'd have to put down another primer to catch the other part, and then another one, to be able to catch the entire one side, see from here,
And I can see you probably take something like this and this, there's only like 1,000.
Another makes sense? Yeah, so like how many is there that's on the technology? But if they have two parts, because if you only need two, it means one at the beginning and G1 at the end. G's huge. So if it only goes so far, remember the technology only attaches the part and copies the rest. We can only copy so much. You can't copy 300 or 400, 500, it's very hard. So you have to like stack your primers so that you capture this part and mix it all together. For now, it's once you run. Can you exclude certain parts and see how they do? Or if the next step will be building.
Yeah, I have much
Okay, looks like everyone's coming to the same point. So, how do you test your primers? Right? So, you guys have all hopefully designed some primers. So, how do you test your selection on the actual genome to see where they are? This is where I think, because we're going to nerd out here, this to me is the most fun part of the activity. So, what you need to do is we want to use the set of primers from your first setting. So, okay, one too many brownies on. Oh god. So we're going to use the set from the first default setting design. So go ahead, if you've already been playing around, go back and make sure you run the first primer design thing, this without excluding any sequencing and with both option left and right picked. We're going to use that default setting to start with. And you also need to, if you haven't already have it open, return to the UCSC browser. So you can see here on the screen from your output, the primers at the bottom. It says left primer, right primer. Right? The length is 20, so the primers reads 20 bases. You can see the sequence on the right part of that. And at the UCSC browser, I want you to choose Tools from the blue menu and choose In Silico PCR. Then what you're going to do is you're going to cut the left primer sequence. So on the screen here where you see the left primer, AT, CC, AC, whatever yours is, and paste it into the forward primer search box on the UCSC browser, and cut the right primer sequence and paste it into the reverse primer search box, and press submit. Yeah. On the browser, under the tools, go to the tools menu on the browser. Blue, everybody have the tools, and then In Silico PCR.
I would have put instead of primer, that was the second primer.
Okay. Once you've done that, you see the screen here at the bottom right, that little, something similar to that. I want you to click on the blue link, and it will actually show you your captured sequence on the genome.
Yeah, it's sure.
We'll show you what you captured on the zoom out a little bit. When you click on the link here on the screen, it says chromosome 5, blah, 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 right? You should see a little black bar at the very top of the screen. If you zoom out a little bit, that top line is what your sequence is capturing, what your primers are capturing, right? It looks like it's probably capturing an exon with the dark bar, the fat black bar being the primers you designed. Are you with me so far? If you zoom out, it's a bit easier to see because you can see more of the gene. You can see that you've captured an exon, or most of an exon. See what I did on top? Very good.
Oh, you've got you out of it.
So when you do that, you need to
Why sorry,
Yeah, because we have to be the same, like,
Okay, so now we're going to get to testing it a bit more. So sometimes you like to see where several primers at once lie on the genome. So maybe you saw with the website you can get 4 or 5 different options for primers. How do you know which one's best? Well, you can play around in a variety of ways to do that. But one way is to test your selection with the BLAT function. So maybe you only want to capture exons, right, the functional parts. So you can use the Get DNA feature to help you with this particular problem, because there's an option in the tool to highlight exons. So if you, same website, make sure you're using the right CamFam 3.1. You can get a list. Remember at the beginning it gave you the top primer for the left, but if you scroll down to the bottom it gave you 3 or 4 more options. So you can put all the left primers into the BLAT window here. So BLAT, remember where you get BLAT from? It's the menu at the top. So I think it's under Tools. And you can make sure you put it as a label of like the greater than 1 and then your primer sequence, because you want to be able to see where they are. You want to know which one is which. So if you recall, you should recognize this format a little bit, because the format you see on the screen is FASTA format. It's the part that requires the little greater than sign and then 1. We did this, I think, last week as well. We were looking at things on the genome browsers. So when you put your potential sequence probes in there, the primer designs are the primer sequencing. You can then hit submit, and it should take you to an output page. And similarly, if you click, when you get to the output page, if you click on one of the links and zoom out a bit, you should see where all the primers are from the left side.
Oh, wait, you really have to zoom out.
Run again. Go on, you should see that.
So when you put all 4 of them in there, you need to zoom out. You might have to zoom out quite a lot to see them all, depending on which primers you put in there. Right? They'll be coded as black bars labeled 1, 2, 3, 4, just like you labeled them earlier. But you're gonna, it's not the link at the top, it's the one that says browser. You only gotta click on one of them and then zoom out.
You know these those two primers of which do we have 14,000? I guess like these ones. If you use these ones, then you would expect to have two of them be going to the other two somewhere else. Oh yeah. That's what ones are good budgets. You have to live out
So, you can use the blue links to look at the results. Hopefully you guys are all doing that. You can use the zoom button in the browser, or you can type the name of the gene in the window to see the context of your primers themselves. Now, unfortunately, I think most of what I saw, the primers are all clustered at one end of the gene. So that's no good, right? You want to capture, so you would have to run the primer design again and see if you get different primers by excluding certain portions of the gene, and using the square brackets like you trialed earlier. Now, for those who are interested in getting more than just 2 or 3 primers that are designed, you can increase the number of results shown by primer 3 by changing the number to return option. So if you change the number to return option, it will give you 5, 10, I forget how far it goes. So we said no. So for the next 10 minutes, I want you to see if you can design primers to capture the exon the main exon that you're looking at. Right? And if you can design a primer to capture that exon, I want you to zoom out on that gene and see if you can design primers to capture all the exons in that gene. So if you're going to design primers to capture all the exons, you need an exon that's in the forward orientation and in the reverse on all the exons in that gene, or at least a handful of them. We'll come around and see how you go. All right?
Places for fish. We're looking at primates to make like.
I do like one.
Especially when you have a long span that is going to be presumably amplified. Definitely don't want.
So we need excellent.
And right now we're just like primates. Every sequence is different, so we don't use specific ones. We just sequence everything. It depends. So you have to do a specific type of PCR to make your fluorescent probe. So regular PCR will just use like regular nucleosides that get incorporated in the like elongation step PCR. When you use fish, you have probes that are either already like fluorescent. I mean, nucleosides that have a fluorescent probe on it, or they have something that can be attached and an antibody can attach to make another to make it fluorescent. So if you think about like if you think about like a chain, yeah. So if you think about like let's say my PCR product is like this. But what fish does, you'll have like different nucleotides that will have like little schmutz on it, so that when they get incorporated, they'll have something that looks like this. And these can be fluorescent molecules, they can be just modified nucleotides in the form. And then when you have them under the right microscope, they will fluoresce. So, does that make sense? Yeah, this is like, say this is the fish construct. Like eventually there's a stage, once you get into it, you get a stage that is like just a single strand so that you can validate that primes and weather, and then that can later depending what your goal is. So for this specific one, we're applying a real for this exercise, we're not actually making fish ourselves. We're just seeing if we can design primers within exons. Just slightly different.
Like my friend,
I'm gonna take it like 12 minutes
Because these aren't the same. So fish is a way of like structurally agitating where things are. And what you're letting out is at the time primes. In the context of like we need to find a region of interest and to make your probes. And your probes are make sure that doesn't have any repeats. When a single strand finishes by itself, it won't really kiss to itself or something. It won't self-heal, and it'll be specific. So you need your probe to be specific enough. It's hard. There's two types of probes. There's primers and the fish probe. Okay. You need your prime sets to make sure that your fish probe is good.
Okay, fun fact, really nice showing you.
Yeah, let's say that you can switch from I have a scaffold and I want to find a picture. So figure out how it places itself right on the left. So I'm going to make pitch probes at the top and the bottom and label in different colors. Yeah, of the scaffold. So the scaffold's like 300 kb. Yeah, consider the scaffold just so I'm going to make fish probes on the top and then take it into colors. And that means if I design my probes properly, I can now know where the top of the scaffold is relative to the chromosome, and the bottom is relative to the chromosome. How's it sitting on the chromosome? And to do that, I'm going to first find a region of interest at the top and the bottom. Then I need to find the region that is free of repeats, because this probe is going to be, from my region, it's going to be a reason where there's going to be a lot of repeats, and I need to make sure there isn't any where I'm designing that probe. And then once I have that region of interest, I have my primers and capture that region. And then now I can amplify that again and have my probes So I've got my region of interest with no repeats in it, right? At the top and the bottom. Yeah. Then I need to have this region here, if the prime is outside the capture.
This symbol, you have a rolling sensors of nucleotide sequences.
And I don't know the specifics, but at some point, when the probes are made, you do PCR again, but this PCR is like incorporates a specific type of fluorescent molecule in some way. Yeah.
Big data, we crash the systems on big data.
I love that.
My dad is on the
Data was stupid.
custody.
Like we had one of my
How it looks like is you have like a slide and you put the probes in and they just go to the genome and like base pair to where they hybridize to where they're going to be. So you're just going to need a lot of them to ensure that it's Yeah, so what I mean, it's like like physically when you're doing the lab work, you just need a lot of
Let's go full.
Oh, that's just, I'm interested in both ends because I'm designing two probes that are unique to the two ends. Yeah. Yeah. So like, I'm going to get a prime set up here, like have this MP3 reader. Prime set down here, like have this Yeah, so it's functionally double-sided, but you'll have a left and right prime object and a left and right. Yeah. So you're not making time to 300 for base fragment scaffold. You have fighting two ends to make a road. Yeah. Yeah, it does.
Yeah, she's scared to ride. I'm too scared to ride over the highways and the different I'm too scared. And also, because I'm still on my you can like ride on
No, just we're only giving it, like, I guess theoretically, you can just give the time sequence and the water sequence. But, yeah. It depends on. So, Brandon earlier said, I don't know, but
hopefully you got a little bit of a flavor of
so fish probes to be like,
don't forget there is a topic session tomorrow, I think, so if you still want to get more practice to this, asking questions will be there to answer any questions there as well. So a couple more things we need to crack on with. So once the genome is assembled, what you have are large sections. So once the genome is assembled, what you have are large sections of nucleotide sequences. Now, you may have successfully scaffolded the sequence reads as far as into chromosome arms, but likely not quite done with that yet. So rarely can entire chromosomes be scaffolded because of the centromeric satellite sequences. And there's some additional links on Canvas about centromeres and satellite DNA. So much as we've placed our content physically using FISH, using primer design, PCR, and sequencing, FISH can be used to locate genes on the physical chromosome. Now, in days long gone by, this method was known as physical mapping. So you may also take a gene nucleotide sequence using the messenger RNA, so mRNA, from another well-characterized species and use BLAST or BLAT to align it with your organism's contigs to find the equivalent contig that houses your gene of interest. Now, on a larger scale, so genome-wide, we can take each of the gene transcript sequences in turn and blast them against our assembly to see which genes align with the contig of interest, the direction of the gene relative to our new reference, and the intron-exon boundary locations. Now, for this purpose, a computational biologist will typically use the set of sequences that are known as RefSeq, R-E-F-S-E-Q. RefSeq sequences comprise validated gene sets for species of interest. Now, a transcript is the sequence of the transcribed portion of a gene sequence from mRNA. It contains the sequences of untranslated regions in exons, but not the intronic sequences. It is shown as cDNA, or complementary DNA, sequence rather than RNA sequence. So in the following exercise, you will use standalone nucleotide BLAST on your class virtual machine, so go ahead and start those, and a single contig from a Tasmanian devil reference genome assembly, along with a cut-down file, a REST-seq file, for gene transcripts to find genes that match with your sequence. Now, as briefly mentioned in week 2, BLAST was one of the pioneering bioinformatic algorithms. It can compare one sequence to another sequence, one sequence to many sequences, or many to many FASTA sequences. Today, you will compare many mRNA sequences from the REST-seq database with one Tasmanian devil supercontig or scaffold. So we're working with TASI devils. This will reveal to you the start and end positions for exons, a question I got earlier today, from the mRNAs relative to the first letter of the subject DNA sequence. In today's case, that subject DNA sequence is a supercontig. Now remember, mRNA sequences are transcribed versions of genes where the introns are removed, leaving only the exonic portions of the gene, so only the protein coding regions. For this reason, we do not expect that each mRNA sequence will align in a single match to a subject sequence because the intronic segment gaps will break the alignment. We may see a single alignment for genes that have only one exon, and there are some of these, but not in this exercise. So there is enormous conservation of gene sequences across species. So the REST-seq genes that we are using do not have to be identified in the Tasmanian devil already. Usually genes are discovered in humans or mice first. Now there's actually enormous conservation or fidelity of gene sequences across species, at least specifically those in the same phylogenetic order. So even though the animals, so humans and Tasmanian devils, are extremely different and long separated in evolution, the protein coding portions of the genes will still be findable in a new animal. We call this process of using genomics of one animal to learn more about another comparative genomics. So hopefully you guys have already started your virtual machines. That's okay. While they are starting, I will go over just a little bit of the background for this. Now, to access a help file for nucleotide BLAST on the virtual machines, all you have to do is type in what you see here, BLASTn --help, right? If you do that, you're going to see a ton of help stuff. It's all quite complicated. There's a lot of things that it can do. However, we are only interested in a couple parameters to perform your alignment. Now, before you start, you will need to copy some additional files to your home directory. The first one being a query file, and this is the file of known gene mRNAs from some other species, such as mice or humans, in a FASTA format, so FASTA format. Okay? And because we're going to try to match these to our devil sequence. The name of the file is here at the bottom, restseq.fasta, and again, it is located in your shared file directory, so once the machine starts, go ahead and copy that over. Now, you also need a subject file, but you should already have this file in your home directory because it was used in this morning's first two activities. It's the Sahar file. So that should already be there. That FASTA file, subject file should already be there. Yeah, you don't write the shared file, just the REST-seq, all caps, not FASTA. Yeah. Don't worry, we're going to write those names of those files on the board. So, there are also 3 other commands or flags you need to know in order to perform this task. Right? The first being the one you see here, perk identity 0.7. The second being out FMT, and the third being out Sahar tabulated blast. Right? You need quality control to do these types of things, and there are many different options for output format. And you also need to tell it where you want to put the files. Okay? So the quality control is the perk identity. The output format is what you see here, output format 6, and that format is actually a tabulated format because it makes it a bit easier to read. And then of course the output file for all the results. Remember, it's a computer, you got to tell it where you want to put everything so it doesn't print it to screen. And so the output file we want to print it to is the Sahar tabulated blast. I will leave this on the screen, by the way. And of course you already have the subject file, and I can see on the boards around here that the query file has already been listed up there. So the next step is just to do this blast. Make sure your external terminal window is wide enough so that it does not wrap the lines for easier viewing. So make sure you make the full screen if you can. Once the output file is there, you can cat it so that you can see what is in there. It is not too large, I don't think, so you should be able to cat it to see what is in there. And keeping with our fishing analogy, I will leave this up to you to figure out what order and how to put these things in there to run this blast. You can use Google, you can use ChatGPT, you can use the help thing to help you generate this output file. If once you get the file done and you cat it and it's been done correctly, skip ahead, for those who have the notes in front of you, skip ahead to the next slide and it will give you a breakdown of what is in each column. I would strongly recommend that you maybe even put it on your computer and open it in Excel, because it's a bit easier to see the columns lined up nicely. And you can see what the output is. The headings are in the next file, or the next slide.
Yeah.
Is it just is that file?
What? You did
That's the file. Yes.
So we did.
I feel like it takes a while.
Remember, guys, you have all the resources available to you. So Google, you use everything you need, trying to help you figure out what order to put these in order to generate this output.
So that website file.
I just saw how I found the RevTech of the mRNA sequences that we're querying.
So that's part of the project.
Yeah.
So it's not just the whole thing, this is
This faucet is the representation of the titanium, and then the rest sets are the mRNA sequences that we're searching for in this gap.
oh, so these are like
Yeah. And then we're searching for that point in this file.
Yeah, but like,
Yeah, to do like something like this real feeding from like basically you know, like to specify what you're talking about. And then the subject that you No, it's less as an exercise in reading, you know.
yeah, exactly. Or like, yeah, the creature has like 7 was like anyway, so I feel like we make this better. I've ordered But yeah, they've got the and they would make it really important for me. Like, yeah, I know this is the one where they have a lot of candidates, like the biggest countries, but they don't look that good on school. They don't
Okay, so yeah, I was gonna have you told me the files so that can you show me what's in your folder right now? Alright, so use LS so that we remember okay, and then okay, so
I need to copy over our two files. So basically, those files, you know where those files are? Alright, those files are in our shared directory, so they're in. So basically, they're in this. So if we go to our shared files folder, and then we go ls, you can kind of see that there's all these files here, and then basically we want to get the ref sec.master and then it's and then so basically we need to copy those files over to our directory. So I can copy. Yeah, because you need to type this space, there needs to be a space between CD and then share, because yeah, otherwise you'll see it as one. Yeah, and then when you and then basically you want to copy the ref sec and master,
They don't have good cards.
for shifting. Yeah. Yeah, they'll send you some security message. Yeah, but it's like it's fine. It's like okay. Yeah, I'm sure I was.
Yeah.
Yeah, and then you want to tell it where you go, where you want it to copy to. So right now, so I want to copy this file into our home directory, which we used to build for. It's like this movie. So yeah, basically you want to like where like set so basically you want to copy and same command, just leave the command.
I got lost and I started bringing the flags. And I had
Yeah, that is kind of the idea, but like you do need to write query, yeah, because you got flag like a file query, and then you want to go yes, ref sec. Because you also need like a subject that you find query the sequences.
yeah, that's the output file.
Yeah. So you're gonna be like it's dash subject, that's the subject. That is flag. That's yeah, again, it's because you didn't tell it where you want it to, because we're housing on this weekly line represents your directory. So, like, it's like a formula, right? With the copy, like, basically is a formula, right? With the copy command, you want to tell it first what you want to copy and then where you want it to get, where you want this file to get copied to. Yeah, that's all correct so far, but you need to tell it where you want it to go to. So,
Just gotta put it in. Just tables over here. How did you get that on?
That's just making a new file.
yeah, create some file.
It's trying to access it. So I might just use the greater than.
Yeah, I'm not sure why. Yeah, not sure why.
You guys have already done that. Just for graphic. Yes, but also how they got so this is what's going to be problems. And that's just going to get back to where they match up to
It's decent. Yeah, that's why we take that. We also want to take the lights. Well, we basically take the lights.
So you can see you're going to need to move this file from the center. So you want the highest match.
See, that's
I want to grab the highest one by open the file, but keep that information. Very last
And now we're going to be doing the G links to can the connotation has changed. I'm watching Charles Berry right now. Well, I love
Oh, right. That's because you commonly try to do this in the shared files directory, which you already have on.
I thought that my first.
Yeah, that's the shared
Okay, it does work. Even though it's like right now, I can just have the class file. Oh, man, you can do
I know, yeah, just such a hero without the E. I remember watching like the first couple episodes and then it was complicated because I least like read some of and I just the one part that I remember was Chainsaw Man. Do you like that? It's okay. It's good. Yeah. I read what? Okay, my boyfriend was the manga right now. I don't even know which manga it is. Oh, you don't know? I'll actually ask you to tell you the next time. We read so much. Alright, so there's this one and he's like oh my god, please, he's such a One Piece fan. Oh my god. So I got him like these figurines recently for birthday, and he was like, "This is the best gift ever." I was like, "Okay." And what about like the shoes that I got? These things you can walk with every day. Like this guy's like set up the figurines and I'm like, this doesn't even make any sense. That doesn't make any sense, but I'll get them because it makes sense. But
Why are you using the use salt? You can use salt and then not just to the specific thing.
It's like bringing in a file, for stuff. It's not like a general sort of that's alright. Okay, so we copied our browser.
What's the name of the manga? I read it like this is how much I've read and he's like, isn't it so funny? And I'm like, it's
these are multiple flags, these are options that tell it like how we want for example this one tells I think it just says that we want like I don't know 6 like for example this one tells us the name of tells us we want the output to go to the file and it's being printed to the screen. And this is and then we're given the name of the file. So basically when we're writing our plot that we clear the flags by one. Identity. And then we then for next one we do a space, and then we do the dash to show it's a new option, and then we write out the next option we want, which is 1.6, and then and then basically one thing we didn't tell you have to do exercise for us to do was that we need to specify a query option so that query, and then with the query that's going to be this file because it's not file. So we then type in and then we have to also include the subject that we are writing our query on. It's going to be this basically has to be very special. Yeah. And then just specify lastly, we need to then tell them what we're bringing on which of the subjects and that. And then that will be once you've done that, will be all done.
Hey, got it?
I'm still like figuring out the from this how to combine with the plus X.
Because with these flags, it's always actually specify one flag usually all the option. So in this case, we'll have to add something.
Also, this is additional. I don't know. Is this taking up a file?
No, because basically what's going on is that this is a flag, so basically the output of cat will go into a sort function.
Yeah.
And a sort function.
If I can tell, like,
I try to see.
yeah, I also don't really, unless we have the place to do it, I will figure it out.
We're actually good.
Oh no, that was fine. The command ran fine.
Right, it's 8. What's the one? 8? Real? You know too much already. Yeah. Yeah, 25. In fact, marketing, but in this case, where it's like you actually
Oh yeah. So this kind of creates a
You have like 4 pages.
C++, create value. Figure out
Yeah, even at the point, like some course, like usually a lot of courses are pretty good. They're like introduction courses.
So for me, we're interested in interesting assessments of math. The highest math school in Toronto has math school. You use that assessment on our instrument. You can look up. This is fancy command. We have to grab that location. This is the same thing that you just did, but you were doing a nucleotide class. And because like yeah, you did on the field browser, but now you're big data and you're on browser. So there's a slight difference here, same input file for the subject, but now you're using coordinate sequence method query file. And your QC is changed as well. You don't want the output to what was like one of these throw that again. And you can locate the rest of the number that best matches yours. Put in the browser and it will give you. And what is this data going to oh, you start that means what is your argument? You're going to use false values. You want to know what's
So if now that's a 6 reading frames. Go pick the one. Now we can navigate to 5,003 frames. Yeah, if you do 3,003, there's technically 3 reading frames if you do.
Because like 3 reading sequences.
Because you read it to you read the data forever. So you get 3 week points and then 3 weeks back. And then obviously every week from 7 to 3 right? Yeah. And then we figure out which one is limit and get the place to so including regions and see which one has the least opportunities. Two of them will have the least opportunities.
That just something like the actual stuff would be yeah,
Oh shit!